All right, so today we're actually going to be starting chapter 16. Chapter 16 is going to be all about probability models. We're going to be transitioning from last chapter where it was more focused along the lines of like, hey, we have created a probability distribution. Now, how do we manipulate the mean, the standard deviation? What happens when you combine two different distributions together? But today we're actually going to be jumping back into how do you actually find complex probabilities. So this isn't like before where we were finding like an individual situation. We're going to instead be jumping into how do you find a complex situation, like if you're taking 10 shots with a basketball, what's the probability that 4 of those 10 will go in? It could be something like, hey, if I'm going to flip a coin over and over until I get a heads, what's the probability that the first heads I get will be the fourth one? So those are the type of things we're going to be looking at in this chapter. Before we go ahead and get started with that, I would like us to go ahead and review some of the complex probabilities we've done before, which is doing the same thing multiple times and seeing if we can find the probability of the entire thing. So if you're looking at this, it talks about rolling a fair die 3 times, and what's the probability of that? It asks that you would roll all 6, that you roll odd numbers. None of your rolls gets a number that's divisible by 3. You roll at least 1 5, and the numbers you roll are not all 5s. So if you are watching this at home right now, go ahead and pause right now and on a separate piece of paper, see if you can answer those questions. So I'm going to give you a few minutes to do that. And by give you a few minutes, I mean you're going to hit the pause button and try to do that on your own. When you're done, go ahead and hit the play button again, and we will go through these answers together. Okay, so hopefully, you have had a chance to answer these questions. If you are struggling with this a bit, that's fine. We're going to go through it. So let's see what we got. First off, it says you roll all 6s. So if we're going to look at this, remember we are rolling the die 3 times. So 1, 2, 3. And we look for the probability of each one individually first. So what is the probability of rolling a 6? Well, there are 6 numbers on the die. So what's the probability of rolling a 6? It would be 1 out of the 6. So we go ahead and say, okay, the probability of getting a 6 is 1 over 6. Then we look about, what about the second roll? Because these are independent, one's not going to affect the number of the next. It's not really going to change the probabilities. So our probability of getting another 6 is again going to be 1 over 6. All right. Lastly, we have one more, so another 1 over 6. And then we need to discuss how do we find the probability of all of these things happening. So the easy way to do that, remember, is by our multiplication rule that states that if you have independent events, you can just multiply the probability of each one of those together. And that's going to give us a whopping total of 1 over 216. All right. Cool. So that's going to be the first one, A. For B, it says what's the probability you roll all odd numbers? This is going to be a very similar, again, we have 3. What's the probability of rolling an odd number? Where odd numbers are 1, 3, and 5. So that's 3 of the 6 options, which gives us the probability of 3 over 6, which reduces to 1 over 2. So each one of those is going to be 1 over 2. And again, we're going to multiply all those together, and we'll get our 1 over 8. All right, next one. It says none of your rolls get a number that is divisible by 3. So here's the deal. We want to find out the probability. I'm going to do this one at the bottom, and then I'll go ahead and erase it in a second. But we need to find the probability that none of the rolls get a number that is divisible by 3. So what numbers are divisible by 3? That would just be 3 and 6, because both of them are easily divisible by the number 3 to give us 1 and 2. All the rest of the numbers do not divide by 3. So we want to find the probability that none of your rolls get a number divisible by 3. So if 2 out of the 6 do get a number divisible by 3, then 4 of the 6 numbers do not get a number divisible by 3. So we can do 4 over 6, or that also reduces down to 2 over 3 for each one of these. All right. And again, we'll multiply the probability of each of those together. So that's going to be 8 on top And 3 times 3 times 3 is going to give us 27 on the bottom. Whoa. 27 on the bottom. Sorry, I messed up a little bit there. And that will be our final guy for that one. Of course, you can always check to see if you can reduce. But let's move right along, get these kind of knocked out. I'm going to go ahead and erase that guy so that we have plenty of room to do some of these other ones that are a little bit more complex at the bottom. Next one says you roll at least 1 5. At least 1 5. So remember, this is where it gets a little bit more confusing. If you're going to roll at least 1 5, we could come up with a ton of different options for ways of doing that. You could roll one of the three as a 5. You could roll two of the three as a 5. And we're not even talking about which order things are falling in yet. So if we want to start considering all of that, that would be a huge probability question. So the little like cheat that we end up doing to get around this is the idea that instead of finding the probability of getting at least 1 5, we find the probability of that not happening at all. And then we simply do 1 minus that answer to give us the probability of all the options that would cause at least 1 5. So when we talk about this, the only way that you would not get at least 1 5 is if none of them are 5s. None are 5s at all. All right. And the way we would do that is by just going through and find the probability that you would not get 5. Well, one of the 6 numbers is a 5. So how many of them are not 5s? That's going to be 5 out of the 6. 5 out of the 6, and 5 out of the 6. All right, so when we are looking at this, we now still follow the same rules as before, which is our multiplication rule. So we go ahead and multiply those three together. All right, and that's going to give us 125 over 216. Now, we don't want that as our final answer. That is the probability of getting all not 5s. So we need to find the opposite of that. So we would do 1 minus that answer. So this is where we plug in that 125. All right, and we would do 1 minus that, which gives us a final answer of 91 over 216. All right. So looking at that, I know that one was a little bit more challenging, but remember when we are usually asked things that have the words at least in it, it's a good hint to try to do that 1 minus strategy instead. So that answer is 91 over 216, and that is the probability that you would roll at least one of the 3 die as a 5. So last one we got here is going to be E, which says the numbers you roll are not all 5s. So here's the deal. This is going to be very similar to just what we just did. It says that we want to know the probability that you are not all 5s. So we could find all the different ways of not getting all 5s, or we can find the probability of getting all 5s and just do 1 minus that number. So again, this is going to be very similar to before, but now we're talking about, okay, the only way we would not get this is if they are all 5s. So what's the probability of getting a 5 for each one? It'd be 1 over 6, 1 over 6, and 1 over 6. We actually have that answer right here because it's the same as rolling all 6s. So 1 over 216. Now, once we get that, we just do 1 minus that answer to give us a final answer for this question of 215 over 216, which means the chances of not getting all 5s is extremely high because there's only one way to do it. So it's essentially going to be way, 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 way up there. Cool. All right, now that we've knocked out this review, we can go ahead and start jumping into the new chapter 16. First things first, Bernoulli's trials. What this is basically setting us up for a bunch of different types of probability problems we're going to be working on. A Bernoulli's trial is kind of just like the first step to defining a larger situation that we'll be dealing with. So you can see here that it says the basis for the probability models we will examine in this chapter is a Bernoulli's trial. We have a Bernoulli's trial if there are two possible outcomes, a success and a failure. The probability of success, P, is constant, and the trials are independent. So, what this is actually telling us is hey, there are certain situations in probability that can be defined as a Bernoulli's trial. In this case, the number one thing is that when you're looking at the situation, there only can be two outcomes, success or fail. All right. Now, in general, that can be really easy or not so clear. For example, if you are flipping a coin, you either are aiming, let's say you're aiming for heads, you either have heads or tails. So that's a little bit easier. There's only two options. But if we're talking a few chapters ago, we did a cereal box question where you could draw a card of a famous person out of it. And we said one of the cards was LeBron James. Then in that case, you would have to label getting a LeBron James as the success, and any other card would be a failure. All right. So, by that definition, it would still fall under a Bernoulli's trial because we're looking at it as okay, I get a cereal box, in that cereal box, I either have a LeBron James or I don't. All right. So then you have a success or a fail. So in order to be a Bernoulli's trial, it has to be set up in that way. A lot of the different probability models we're about to look at are going to be based around the idea of assuming it's a Bernoulli's trial. The second thing is that the probability of success has to be a p, constant. That basically just means like, hey, if the chance of me getting a LeBron James is 20%, then it needs to be 20% every time I get a box of cereal. Otherwise, it would just be changing every time, and there wouldn't be a set situation we could find the probability of. And the last one is that it is independent. All right. So, independent meaning getting one cereal box with LeBron James isn't going to change the probability I get LeBron James in my next box. Okay. So, that last one, the independence requirement, is actually the least important of them because you actually can get around it. It says one of the important requirements is the independence, but when we don't have an infant population, the trials are not independent. But there's actually a rule that allows us to pretend we have independent trials anyway, and it's called the 10% condition. It says that Bernoulli trials must be independent if that assumption is violated, it is still okay to proceed as long as the sample is smaller than 10% of the population. So, what does this mean? It means if we go back to our LeBron James sample that we were talking about before, if I'm looking at all the cereal boxes that we're drawing from, if there's like 1,000 cereal boxes and we're going to test our theory on five of them, all right, when I draw one and then either get LeBron James or not, and then draw the next and get LeBron James or not, it's still about a 20% chance of getting LeBron James every time. Now, it's a little bit different if there were only 10 cereal boxes total and we knew that 20% of them had LeBron James. If there's only 10 boxes and I draw one box and it's LeBron James in it, well, now I know that I removed one of the two boxes that had LeBron James. So when I draw the next box, it's going to change my probability because my sample size is so small. So in that case, drawing like 3 of the 10 would be over the 10% condition, so it would no longer work. Okay. So the 10% condition is basically just saying whatever the number of trials we're going to actually do, it has to be less than 10% of all possible trials. Now, there are some situations where you'll never reach all possible trials, like flipping a coin, for example. You can flip, 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 and you could flip forever. So you can't really claim that a certain number of flips will be 10% of the whole population. All right. So, moving along with that in mind, as I said, Bernoulli's trials are a general term, all right? But we're going to look at specific models for this chapter. The first model we're going to look at is called the geometric model, all right? And it's going to come from a question like this. It says, Postini is a global company specializing in communication security. The company monitors over 1 billion internet messages per day and recently reported that 91% of their emails are spam. Let's assume that your email is typical 91% spam. We'll also assume that you aren't using a spam filter, so every message gets dumped into your inbox. And since spam comes from many different sources, we'll consider your messages to be independent, as in one is not going to affect the probability that the next one is spam. Overnight, your inbox collects emails. When you first check your email in the morning, about how many spam emails should you expect to wade through before you, or in discard, before you find a real message? What's the probability that the fourth message in your inbox is the first one that isn't spam? So there's two questions here. The first question is asking, all right, on average, how many emails should you have to look through until you find the first one that actually matters? The second question is saying, what's the probability that the fourth one, that one on the dot, the fourth one, is the one that makes a difference? That's the one that is actually a message. All right. So this is what we call a geometric model. A single Bernoulli trial is usually not all that interesting, but when we're looking at it in the general picture of a bigger problem, it's where it becomes extremely useful because it allows us to use formulas to find these probabilities. A geometric probability model tells us that the probability for a random variable that counts the number of Bernoulli trials until the first success. Great, cool, awesome. As you guys know, sometimes it's a little bit better to not use the book's definition. So, what is a geometric probability model? Geometric probability model, what you should be writing down in your notes, is when you're doing a Bernoulli trial over and over again until you get the first success. So, it's any situation where you are going to do a repeated trial where you have either success or fail, and you're going to do it until you get the first success, and then you stop. So there's not like a set number of trials you're going to do. You're just going to do a bunch of trials over and over and over again until you get that first success. All right. It says at the bottom there, geometric models are completely specified by one parameter, p, the probability of success. So, for example, if we were looking at this problem, it said that the chance of getting a spam was 91%. So the probability of getting a useful email would be 9%. So you would define one of those as our success. In this case, you would probably want to consider the not spam email, like the actual useful one, to be your success. So RP would be 9% or 0.09. All right. So let's look at the formulas that are associated with this. So I know this looks very scary at first, but do not let these formulas freak you out. They're actually a lot easier than they look from what we first see. So starting off, it says our three variables we're using here is a p, a q, and an x, where p is your probability of success, q is your probability of failure, and x is the number of trials until the first success occurs. So if we're talking about the situation we just saw in the question, it told us that, hey, the chance of getting a good email, all right, so we'll label a good email as our success, our P, is going to be 9%. We already talked about why, because if 91% of them are bad, that means that 9% of them are good. All right. And then in this case, our Q, the probability of failure, would just be 1 minus that, which we already said was going to be our 91%. All right. So X changes depending on what the question is actually asking. So if I asked you guys, hey, I want to know the probability that the third one, the third email you open, will be the one that is not a spam, like an actual email, then in that case, X would be 3. Or in our question, it mentioned 4. So if I was going to set up, how do you find the probability that the third one would be our best, like our actual first not spam thing, then I would just fill out the formula like so. For Q, we already said at the top that that's going to be 0.91. And then I said we want to know about the third one, so we'd do 3 minus 1. And then we'd multiply that by our 0.09 for a success. Okay. So if you actually follow that through and do that all the way out, that would give you the probability that the third one will be the first success. Now we're going to actually like plug out the numbers and see what comes up here with the number 4 in a second when we do the question that was asked. But for right now, just know that's how you would set up the problem for the third one. What is this expected value down here at the bottom? The expected value down at the bottom is saying, okay, on average, if I'm doing this situation over and over again, how many emails would I expect it to take before it actually is a useful email? And it says in order to find that number, which can also be represented as the mean amount, the expected amount of emails, you can find that by just doing 1 divided by p. So in this case, that would just be 1 over 0.0 9, which is actually extremely easy to find. So if we want to know how many we should expect to have to open before we find a useful one, then there it is. It's just 1 over p, and it gives us the answer. And again, we're going to do that in a hot second on our actual example question. So let's go through doing this. So the first thing says about how many spam emails would you expect to wade through and discard before you find a real message? All right. So we already mentioned this. This is saying how many would we have to expect before we found a real one. So this is talking about our expected value. All right. And that means that our expected value, we already said, is 1 divided by p. Okay. Which means that all we're going to have to do here is 1 divided by 0.09. Now, when you do 1 divided by 0.09 in your calculator, that actually gives you 11.1. So, what does this mean? It means that if I were to open my email on any given day, with the amount of spam I get, I would expect to have to go through 11 emails before I found the first one that was not a spam email. All right. What if I said I didn't want to wait for 11 whole emails? Okay. Then in that case, I would be answering our second one. That is, what's the probability that I could do it in 4? Just 4. All right. So again, we go back to what our formula was. Our formula stated that we're going to do the probability of finding x equal to 4 is going to be the probability of failure to the 4 minus 1, which 4 was our x in this case, times the probability of success. So in this case, that would be the point, well, keeps doing that, sorry, 0.91 to the third power times 0.09. Now, this shouldn't be surprising because we actually know how to find this the long way, right? If we didn't have the formula, what would we do in this situation? Well, we would say, what's the probability that the first good email we got was the fourth one? So that means that we would do 0.91 for not getting it, 0.91 for not getting it, 0.91 for not getting it, and then on the fourth email, that would be the first one where we do. So this actually is not a new situation. It's one that we already have done, all right, and we would do the same thing. Now, if you actually plug either one of these into the calculator, all right, both of them should give you the answer of 0.0678. Now, what does that mean? It means essentially that there is a 6.78% chance that you would get the first good email on your fourth message. Now notice 6.78% is extremely small, but of course it's extremely small because we already said we shouldn't expect it on the fourth one. We should be expecting it all the way on the 11th one. So it would be very rare we would see it in the first 4, all right? Also, there are a ton of emails that it could be the first one on. So these probabilities are all going to be remotely low because we're looking at each one individually. So what's the probability of it being a 3, a 4, the 5th one, the 6th one, the 7th one, the 8th one, the 9th one, the 10th one? So there has to be a probability for all of those. So these numbers are going to get pretty low so that we can have some type of probability for each one. Now, the further we get away from 11, since 11 is the average, the further we get away from 11, the lower those probabilities will be. Just kind of like the normal curve, our highest chance of success is going to be directly on that 11. But then as we move away from that 11, all right, that probability is going to get lower and lower and lower. So by being over here at the 4, we're going to have a much lower percent than if it was right on the 11. All right. This finishes up this question. And the next thing that we're going to be looking at is how do we do this on your calculator? we're actually going to hold off on doing this on the calculator until tomorrow. So I know that this is the first day of doing one of these videos all the way through. I really hope that it wasn't too painful. I tried to keep it under a half hour because remember, usually we have, 50 minutes of class. So think of this as a 20-minute bonus that you guys didn't have to worry about. So I'm going to go ahead and post a question on Schoology for you guys to answer. That way you can show me if you actually know how to do any of this. It'll be just like the example we did together. And obviously I have my son here with me now who decided to join me in the middle of the video because he was throwing a fit. So again, we're going to pick up on how to do geometric problems on the calculator tomorrow. But for right now, go ahead and just try the one question on Schoology that's going to be based off this. Cool. Thank you guys. Have a wonderful day.